In this video, we're going to prove two important limits that allow us to do calculus on trig functions later on. So the first limit is the limit of sine theta over theta as theta goes to 0, and that turns out to be 1. And our second limit is the limit of 1 minus cosine theta all divided by theta as theta goes to 0, which turns out to be 0. Now, neither one of these limits is immediately obvious. So for the first one, the sine function approaches 0 as the angle becomes small, giving us a 0 over 0 indeterminate form. And for the second one, the cosine function approaches 1 as the angle becomes small. So I have a 1 minus 1 in the numerator. Again, we're approaching a 0 over 0 indeterminate form. So to get these proofs done, we're going to return to the unit circle where the sine and cosine functions were originally defined. So here we are on the unit circle. That's a circle of radius 1. And recall that the definition of sine theta for some angle theta is that it's the y-coordinate of this point on the unit circle inclined at an angle of theta relative to the positive x-axis. And the definition of the cosine of theta is just the x-coordinate of that point. So if we think in terms of side lengths of this triangle, the base of the triangle has a length of cosine theta and the height of the triangle is sine theta. And for our geometric construction, what we're concerned with is actually the area of this triangle. I'm going to call that A1. And the area of a triangle is just 1/2 base times height. So A1 is 1/2 cosine theta times sine theta. Next, we consider the area of this sector of the circle that subtends an angle of theta. And the idea with getting an area of a sector is we just look at what fraction of a circle is taken up by this sector. And that's the angle theta divided by 2 pi, since the angle in the entire circle is 2 pi. So we think of that as the fraction of the circle taken up by this sector. And then if we multiply that by the area of the entire circle, which is pi r squared, but the circle has a radius of 1, then we'll get the area of the sector. So these pi's are going to cancel out. And of course, 1 squared doesn't change anything. And it turns out the area of this sector is going to be just theta over 2. So I'm going to call that A2. And we notice the entire triangle A1 is contained within the sector A2. So we know that A1 is less than A2. Next, we're going to construct a second triangle that completely contains that sector. And notice that the base of this final triangle is equal to the radius of the circle. So the base is equal to 1. And we want to express the area of this thing because we know it contains the area of the sector, which contains the area of the small triangle. So to get the area of this final triangle, we need the height of it. And I'm just going to call that question mark just for a moment. And I know that the tangent of my angle theta is going to be opposite over adjacent, which is question mark over 1. And we just discovered that that question mark is actually equal to the tangent of theta. So now we can write down our third area. And this one contains the previous two. And this is just going to be 1/2 times the base of that larger triangle, which is 1, times the height, which is tangent theta. In other words, just 1/2 tangent theta. So there's a string of inequalities relating these areas. The area of that small triangle, that's less than the area of the sector, which in turn is less than the area of the large triangle. So we plug in these areas and we find that 1/2 cosine theta times sine theta is less than theta over 2, which in turn is less than 1/2 tangent theta. We can multiply through by a 2 and get rid of all those denominators. And then what I want to do is divide all 3 parts of this compound inequality by the sine of theta. So we arrive at this new compound inequality. Cosine theta is less than theta over sine theta, which in turn is less than 1 over cosine theta. And what we're trying to do here is prove something about the limit of sine theta over theta, but in our expression we have the reciprocal of that. So we can take the reciprocal of all 3 parts of this compound inequality. Now taking the reciprocal simply reverses the direction of an inequality. And now we've just about got this proof because we already know the limit of the cosine function as theta goes to 0 is just 1. So these limits on the left and right hand sides are going to be unambiguously 1. Then we can invoke the squeeze theorem to say that the limit of sine theta over theta itself must also be 1. But to be totally clear here, the type of limit that we're taking right now is one-sided. We're looking at a limit as theta goes to 0 from the right. In other words, theta is positive, but getting closer and closer to 0. So we have that the limit as theta goes to 0 from the right of 1 over cosine theta. That's going to be equal to 1 because cosine theta is approaching 1. We also have that the limit as theta goes to 0 from the right of cosine theta is equal to 1. And then by the squeeze theorem, this implies that the limit as theta goes to 0 from the right of sine theta over theta is also 1. So in a sense, we're halfway done with this derivation. But the second half mimics what we just did completely. There's just a couple adjustments we have to do for minus signs. And the goal in the second half, of course, is to show that the limit as theta goes to 0 from the left gives us the same value of 1, and therefore the ordinary limit is also 1. So here's what it looks like as we start with our second half of the proof. And we're already starting to make some minus sign adjustments. Remember, the sine of theta is the y-coordinate on the unit circle corresponding to an angle of theta. Well, if I take a negative value of theta, in other words, I'm below the x-axis, then the y-coordinate is negative there. So the sine function is a negative quantity, but I'm trying to talk about geometric length in my diagram, and that has to be positive. So the geometric length of this vertical side is actually negative sine theta. So when I start talking about area here for this triangle, again, I'm going to call that A1. That's going to be 1/2 times the base times the height, which is negative sine theta because the height has to be some positive quantity. And I can write that as negative 1/2 cosine theta times sine theta. Next, we look at a sector that completely contains that small triangle. And we do the same sort of reasoning here. The area of a sector is given by the fraction of a circle taken up by that sector, which is theta over 2 pi almost, multiplied by the area of the circle itself. Now, the reason I said almost is because theta is actually a negative number here, but this area has to represent a positive quantity. We're talking about geometric area. So I actually have to supply a minus sign to this one as well. Now the pi's are going to cancel out, and I find that my area of a sector is just negative theta over 2. Finally, we construct the large triangle that contains the sector, which in turn contains the small triangle. And we run into a similar issue with minus signs here. The side opposite that angle is still the tangent of theta, but if we just said tangent theta, well, the tangent of theta is negative when theta is below the x-axis like this. So we have to put in a minus sign to correct that so that we can talk about the geometric length of that side. So the length of that side is actually negative tangent theta. And again, I'll call the area of the large triangle A3, and it's 1/2 base times height. The base there is just the radius of the unit circle, so it's 1. And the height is negative tangent theta. So we end up with negative tangent theta over 2. So all the corrections have been made for the minus sign issues here. And again, I get a string of inequalities corresponding to geometric objects that are nested within each other. I see that A1 is less than A2 is less than A3. And again, we can multiply through by a 2. We can also multiply through by -1 if we keep in mind that we have to reverse the direction of all the inequalities. Then we're going to divide by the sine function. Now I noticed a mistake as I was editing this video. Remember, the sine of theta is a negative number in this case, so when I divide by that, I should be reversing the direction of all the inequalities. So for the next 2 steps, I have my inequality signs pointed in the wrong direction. Now that doesn't change anything about the mechanics of the proof, but you should make a note of that so that it's 100% correct. And we take the reciprocal again. Remember, that reverses the direction of inequalities as well. And so now all we have to do is invoke the squeeze theorem again. But this time when we're talking about our limits, we're talking about theta approaching 0, but theta is a negative number. So this is the approach from the left. And as theta approaches 0 from the left, the cosine function approaches 1. So this first limit is going to give us a 1. And again, the limit of the cosine function itself as theta approaches 0 is just 1. So by the squeeze theorem, the limit as theta approaches 0 from the left of sine theta over theta is also equal to 1. So now we've got our left and right limits agreeing with each other, which implies that the ordinary limit exists and is equal to that same value. And that gives us our first limit. Again, this thing is going to be critically important for figuring out how to do calculus on trigonometric functions. So our next goal is to figure out the limit of 1 minus cosine theta over theta as theta approaches 0. And thankfully, we don't have to do a fresh geometric construction for this. We can just manipulate this algebraically and use a trig identity. So I see that 1 minus cosine theta in the numerator, and I'm immediately thinking, let's multiply that by the conjugate, because that's going to give me a 1 minus cosine squared theta, and there's an identity for that. So we multiply the top and bottom by this conjugate. And in the numerator, again, by design, the cross terms are going to cancel when I apply FOIL to this thing. And I end up with just a 1 minus cosine squared theta over theta times 1 plus cosine theta. Now 1 minus cosine squared theta can just be rewritten as sine squared theta. And now I'm going to split this thing apart because I noticed that I could build a sine theta over theta piece of this, and then there would be a leftover part with a sine theta over 1 plus cosine theta. And we know from the limit laws that the limit of a product is the product of the limits, so we're free to rewrite this thing as a product of two limits. So I'm going to pull 1 sine theta out of the numerator. I'm going to pull the theta out of the denominator. And I end up with the limit as theta goes to 0 of sine theta over theta. In other words, our first special limit, and we know the value of that thing is 1. The leftover pieces here are a sine theta in the numerator and a 1 plus cosine theta in the denominator. And again, that whole limit out in front is just equal to 1, so we can just replace that with a 1. And then we try to figure out the second limit. Well, there's no problem caused by direct substitution of theta equals 0 here. I don't have any kind of indeterminate form going on anymore. The sine function is approaching 0, and the cosine function is approaching 1. That means the value of this limit is going to be 0 over 2. In other words, 0. So there's our second important trig limit. And again, this is going to be a critical piece of learning how to use calculus on trigonometric functions. So in the next video, we use these limits to prove the derivative formulas for the sine and cosine functions. I'll post a link to that video at the upper left, and I'll see you there.